All right, so thanks. It's very nice to be here. What does compressed sensing mean? What are we modeling? We've seen a lot of talks over the last day or two, well, since I've been here at least, where people have been talking about inference problems, recovering things, and there's a variety of assumptions that are made, whether you're looking at kind of a discrete world, a coding world, different levels of uncertainty or uncertainty. So to me, compressed sensing is kind of the analysis of inference problems where there's some degree of interaction between the components you're trying to understand. There's some degree of structure, so you're not just going to model things as being uniform on a sphere. And reconstruction is nonlinear typically, so you're going to go beyond kind of the classical analysis that's just dominated by properties of when you have a matrix, okay, what's the largest and smallest singular value. So this problem, right, and I think it's shown up a lot in this area called compressed sensing, but it's not a new problem, and it's really, I think, the value comes from its ability to model things that people care about in different areas. So for instance, in signal processing, right, and maybe this is kind of one of the original selling points of compressed sensing, is actually can be viewed as a data acquisition scheme itself. Right? So the argument being that if you're going to measure a signal, but instead of observing the signal directly, you acquire somehow linear measurements. If those linear measurements have a nice property, you know something about the signal, then you can get away with fewer measurements than you might need otherwise. And that's kind of the original slogan. But the problem, is one models it up this way. It's a system of noisy linear equations. That's also the problem that was studied a lot of times in, say, communications. And in particular, a lot of the analysis that people have come to studying this with random matrices is actually a model that's inspired by the physics of multi-antenna systems. Right? So if the fading coefficients are roughly independent, actually a random matrix models the problem you're trying to solve, and there's a lot of math that was developed in that context for communication that had nothing to do with sparsity. And that's also, in my mind, relevant here. Statistics. Here the idea is that you're trying to come up with not necessarily an explanation, but a model that allows you to relate kind of features you see to responses that you care about. Right? Which genes are associated with cancer? You don't necessarily believe it's a linear model, but you do know that linear models are very useful for helping you identify important features and say things you care about. Right? So it's an important modeling aspect. You need to understand how these models work. And also, if you think about this as kind of the first order expansion of an interesting function of the data, right? I'm going to do something linear and add on some noise, right? That's really quite basic, and I think a lot of the tools and algorithms, right, that come in here, the analysis, the idea of how do you solve these optimization problems, these are very relevant in areas like machine learning, where the ultimate goal is get algorithms that work well and you can say something about. So that's my spiel about what is compressed sensing. I think I mentioned sparsity once, and that was to say that in communication you don't need it. But sparsity is a very poignant example of a type of structure where you can say kind of, I think, the first kind of interesting things. So the type of model you want to study really depends on the applications. And I think some of the things we might have seen is where these deterministic models, where the signal is deterministic, you want to give these kind of worst case guarantees. That's not so much what I'm going to talk about here. I'm more interested in typical behavior with respect to some kind of general or random setup. And again, you can think about as the signal random. Is your measurement matrix random? These choices can be made and based on the type of analysis you want to do, the problems you think about making sense. Sometimes they are justified, sometimes they're not. So I think it's always good. What I like the idea is if you can make some assumptions about, say, a random matrix, and if you can make a precise prediction about the behavior, well, then you can try and test it by actually generating some random matrices and seeing if it's the same. And then you can ask, well, does this prediction I made for a random matrix also correspond to non-random matrices that I see in practice? If the answer is yes, then it's something that's useful. If the answer is no, you need to revisit your model. So what I'm going to study here is kind of this one that's, I think, very amenable to precise analysis. And this is kind of the playground for an information theoretic analysis, where I'm going to think of the signal as being generated randomly with some IID prior. And I'm going to think of the matrix as being a large IID Gaussian random matrix. Right? And in my mind, what I'm thinking is that I want this matrix to kind of model typical behavior of some large dense matrix. And so my hope is that saying IID Gaussian will capture that. And the IID prior, right, is actually going to capture a rich variety of signals if you choose that IID distribution to have interesting properties. So what's interesting, well, I don't want to say whether I'm not interested in just saying, modeling something as discrete or continuous. I think interesting happens when it could be partly discrete, partly continuous. So some probability you're drawn on a finite set with some probability each entry is drawn from a continuous distribution. Sparsity is a special case of that, right? Sparsity says with some probability you're exactly 0. If you're not 0, what are you? Well, that can matter a lot. And I want to understand how that matters. All right, so this is the setup. The quantities of merit here. What do we care about? Well, I'm going to define kind of two properties, the mutual information, the MMSE. These are related to each other. And, well, of course, it's not everything you could think about. Kind of in the setting I will talk about, these are somehow sufficient statistics for inference. So let me justify that in a second. And again, it should be clear, when I use MMSE, it's the same type of creature notationally as mutual information. That is to say, you take of what is the expected squared error conditioned on the data, and then take the average with respect to the distribution on the data. So there's nothing random about either of these quantities, though the notation indicates the conditioning, the expectations taken with respect to that. So to kind of set up, here's the, so again, if the signal's Gaussian, you can kind of get closed form expressions for these. And what I'm plotting here is the mutual information in this setup with a Gaussian signal as a function of the random matrix. And the idea here is that when the matrix is, and here with m is equal to n equals 3, so you have a square matrix. So when it's small, you see is the blue means that you have some expectation, but it's kind of random. But once we get up to n equals 50, all this randomness in the matrix really doesn't matter so much, right? N equals 50, it's not very big, but of course you have 50 squared components driving this. But you converge very rapidly to a non-random limit. So the analysis I'm thinking about is saying we have a large problem characterized by a large random matrix, and I believe that much of the randomness is going to go away, and it's going to be characterized by, it's going to be very close to some deterministic value. And to study that value, I'm going to study the limit where n and m go to infinity with a fixed ratio comparable to my problem at hand. So this is not a scaling result. I'm not saying, there's not kind of saying that, n is equal, or m is equal to k log n or anything like that. I'm going to say there's a fixed ratio, and I want to understand, I think that things are large enough that that behavior at that single problem size is characterized by the asymptotic limit. And so by that I mean, I'm just going to blow things up, but keeping the ratio fixed, and then think about, do these converge to limits? And these are denoted by the script I, where delta now is this ratio. There's different parameters you could look at in this compressed sensing model. But the driving one we'll think about today is delta. It's how many measurements per unknown signal value do you have. And we'll scale the SNR in kind of the way that if you increase delta, you're just getting more measurements. You can only do better. So as delta gets bigger, mutual information is increasing. As delta gets bigger, more measurements, MMSE is decreasing. There's nothing else to it. All right, so what can we say about these limits? And one of the first things I'm going to do is give a very, very brief overview of the replica method from statistical physics as applied to mutual information. So my expectation is, and I know some of you have seen the replica method and understand it fully. Some of you have probably never seen it before. So this will be 2 slides that gives everyone at least a context with which to understand the basic principles of it in this probabilistic setup. So the first is that mutual information, right? I can always just express it as the difference in differential entropy between my measurements given the matrix and the measurements given the matrix and the signal. Well, the second term is not very interesting. I know the signal, all I have left is noise. That differential entropy is well understood. The first one is hard. What is differential entropy? Well, you can think about it as the expectation of a random variable. That random variable is the log of the density evaluated with the random realization of the signal in the matrix drawn according to their joint distribution. Okay, so the name of the game is just compute an expectation. Well, there's different ways to represent the expectation. One of the things we know is the expectation is it's the first moment, so you can also use the moment generating function. It's also the first cumulant, so you can just use the cumulant generating function. Right? So the definition of cumulant generating function says this gives you cumulants if you take the derivative at 0 and evaluate. So the first derivative, right? But of course, since the cumulant generating function is also equal to 0 at 0, it's just the limit as the parameter goes to 0. So here I'm using lambda to denote the log of the moment generating function. And so definition of cumulant generating function tells you this is another way to write the expectation of a random variable. In statistical physics, this is called the replica trick. All right, so now we already have the first part of the replica method, the replica trick, or the definition of cumulant generating function. Second, we need replicas. The idea is that if you want to evaluate this cumulant generating function, if you choose integer arguments, you can then just playing games with expectations, write it as many independent copies. We've seen this before. When you want to take the square of a sum, you can write it as the product of two sums with different variables. And the key reason this works is that the moment generating function says take the exponent of your random variable. When we take the exponent, though, of this random variable z, it was defined as the log. The exponent cancels out the log. And now we're taking an expectation of a density, which you can use just, now again, just tricks of rewriting things as products of expectations. The last step. We have some expression for integer values. It's a statement of large deviations theory. What happens as you grow the dimensions large? Can you say about the limiting behavior of this? And note that I'm dividing by 1 on n. Okay? So this is a 1 on n log type object. And so large deviations theory says you get some rate function. Most unlikely things happen in the most likely of ways. So you want to find the minimum or maximum, depending on your point of view. And so that's where the replica symmetry assumption comes in. You have something that's actually a matrix valued argument. You want to evaluate it, and it says, OK, at what point are you going to find these maximum that are meaningful? So the devil's in the details, and this limit's problematic because it's not clear you can take this limit and then swap it and then take the parameter going to 0. It's also not clear that this assumption of where you're evaluating this minimum is correct. Right? So there's cases where you can show it is correct, and there's cases where you can show kind of that it's more complicated, and you need to take you have some function, and can you kind of guess the solution lives on a certain set of solutions, or do you have to explore over a bigger set? All right, so takeaway, replica method has been used for a long period of time, develops lots of powerful techniques. Often they're shown to be rigorous later, but by itself, without verifying whether these assumptions are correct, it's not a rigorous method. And all right, so that's all I'm going to say. That's 2 slides, hopefully to give you some flavor. So back to our problem. What happens when you apply the replica method to this problem? And what I point out, right, is it has IID signal prior. So kind of in the information theoretic hope here is that you can get some characterization of these limits. That's a so-called single letter characterization. That is, it only depends on kind of the relevant dimension delta and kind of the II and the single distribution of a single random variable in your signal. And so indeed, that's what we have. And so I'm going to give you what the replica method says as the kind of the prediction for the performance of compressed sensing. And so here are the citations. So again, the replica methods, there's a long line of work leading up to it. Kind of the first work applying it to this setting was done by Tanaka, who was looking at binary signals under this context of CDMA. So again, this is wireless communications. And then there was a nice generalization of these results by Go and Verdu, where they kind of worked it out for very general distributions. And so the idea is that we need to define these single letter functions. Right? So I'm defining I sub x of s and MMSE sub x of s. Here, s is your effective SNR parameter. But other than that, they are functions of a single random variable drawn according to the distribution of your signal and a single noise variable. So these are the kind of mutual information and MMSE of your random variable under additive noise at SNR level s. And you can, for any distribution, right, you can just compute these being a 1 or 2-dimensional integral numerically. So here's the statement. It says if you run the replica method under the assumptions, you get this nice characterization. The first is that the mutual information is the minimum of this term, which involves the first part involves the single letter mutual information. And the second one involves something that depends on delta. So the 2 things that matter, your prior signal distribution P of x and your ratio delta, these show up here along with this minimization of an auxiliary parameter. And then the second statement says is that the MMSE you're going to get is the MMSE function evaluated at the minimizer of this function. So that's all there is to it. And when I first saw this, I thought, well, that's pretty amazing that you can take this complicated thing and get such a simple expression at the very end. So let's think about this. I'll show you what it looks like in a second. But let's just first think about what are some properties we have from this relationship. Well, one of them is there's this, it's gotten some popularity. The relationship between, in the scalar sense, the derivative of the mutual information function under additive Gaussian noise is related to the MMSE. Okay, this is a general statement. So this is for additive Gaussian noise, but holds for any distribution on X. And it's not really new in the sense. This has also been known in the statistics literature, in the relationships between Fisher information for a location parameter and differential entropy. So again, there's a lot of these relationships which are kind of understood, these special properties. What's nice about this is that if we plug it in, right, we know that the minimizer of this function Right? This function is continuous in S. So at the minimum, the derivative, we have to say what's the derivative, set the derivative equal to 0. So whatever this minimizing value S star is, the top term in brackets evaluates the derivative, evaluates to 0. We can plug that back in, and we in fact see then that the replica solution here satisfies a certain fixed point equation. And that just comes from evaluating the minimizer, plugging the optimality condition of the derivative being equal to 0, and using the fact that we know what the derivative of the mutual information gives us the MMSE. So in fact, if you go to the paper by Galen and Verdu, and you look at the theorem, it says, if you want to know what the limiting MMSE is, find the solution to this fixed point equation. That's what it is. Okay. And so I did that when I first read their paper. I said, oh, all I have to do is solve this fixed point equation. OK, I'll go and do that. And so what you do is here, so I had picked a distribution here. It's the same distribution I'm going to use throughout. It's basically with something called the Bernoulli Gaussian one. That has to say that my distribution has a point mass at 0 with some probability. Or if it's not at 0, it's a Gaussian. So you can also think of it as a Gaussian multiplied by a Bernoulli random variable. So this is the set of solutions to that fixed point equation. And you can just, again, plot it numerically. It's a little hard to see what's going on here, so I'm going to change up the y-axis. So the x-axis is my ratio of measurements, this delta parameter. Okay? And so let me just rewarp the y-axis. There. So now it's just I put it inside of a log in a way that makes this look nice. And I remember I plotted this, and this is what happens. Great. So now we have the MMSE as predicted by the replica method. Right? And what happens as we get more measurements, it's, wait, what happens? There's something very crazy going on. There's multiple solutions here. So the theorem said, find the solution. That's what the answer is. And if I'm here, here's my answer. If I'm to the left of these dotted lines, there it is. But if I'm in here, there's 3 possible answers for the MMSE. So I guess the possibilities is that maybe there's some random variables supported on each of the 3 possible solutions for a given delta. Maybe it's always the upper one, maybe it's the lower one, right? Well, if you remember, when I stated, the actual form I stated says that the mutual information is the minimizer of some function, and the MMSE corresponds to the argument that minimizes that function. So it turns out that if you choose this, you have to go back and say, which solution is it? It's the one that's the minimizer of the mutual information. It's a global minimizer of this other function. And that's actually in the Gaussian and Verdu paper, but it's kind of like an after effect. In the case of multiple ones, choose the one which minimizes this approximate free energy. So if we do that, it turns out that what the replica says is that we're going to have a single jump here. We're going to be along this top line, then at some point we're going to jump down to the bottom. And what's nice, right, is this pink curve satisfies what I said. It is a function that is decreasing in delta. We get more measurements, right? Our MMSE goes down. And it just so happens that the way in this, I chose the scaling correctly, that another way of interpreting where it jumps is when the areas to the right and to the left are equal. Right? And this has a property that we'll see later on, has a nice interpretation. OK, so the replica says you're on this curve and you jump at a certain point. All right, so that's pretty cool. But this motivates the question, is the replica method correct for this problem? And again, there are cases where the replica method has been applied, and you can verify using other tools that it is correct. There are also cases where it's been applied, and you can show that maybe by itself it's not correct. Maybe you need one replica symmetry breaking. Maybe you need more. And then maybe even with all of that, it still doesn't work. Right? So that it's not known in general. But there are many special cases. For instance, as I mentioned before, if your signal's Gaussian, life's good. Right? If your signal's Gaussian, you can characterize the mutual information MMSE just as a function of the spectral distribution of your matrix. What's going on there is that in the case of Gaussians, it agrees with everything the replica method says. You never have multiple fixed points in your expressions. Everything's very clean. And just using basic random matrix theory, this was done before 2000. Now, again, if you change up the matrix model, right, you say, well, what if I had a very sparse matrix, right, inspired by some of these kind of like locally tree-like properties? Well, again, then there's some work that says, yes, you can show that for certain cases it is of interest. So there's a very interesting paper, again, so this is by Creda and Macri, where they look and they say, OK, what about, can you say something about, is the replica maybe an upper bound or a lower bound on limiting mutual information? The idea here is to use an interpolation method, where you find a path between your system defined by this large random matrix to a system that's that's easier to analyze and corresponds to that limit. And then you say if everywhere along that path I'm only making changes which would increase it or decrease it, depending on which way you're going, then I will get an upper or lower bound. So this is an interpolation type method which is used in the statistical physics literature. But again, so that's one type of information. Another thing is that what if you study a certain algorithm? And so we heard a lot about message passing, and I guess Henri was talking about with factor graphs. And one of a very fascinating result was kind of this analysis of an approximate version of message passing on dense graphs, such as those generated by this IID Gaussian matrix. And it turns out that you can use AMP to show the replica method is right sometimes. And by that I mean, it turns out when you do AMP, you get a state evolution that you can track. All right, and it's not the one I gave you here for the replica method, it's a different one, but when you analyze the fixed points, they correspond to the boundary of the same curve. So another way of saying it is that if you are asking about the MMSE you get using approximate message passing, you can show that you're always getting the upper envelope of this figure that's seen here. So, translation, if delta is large, you are getting the optimal MMSE. If delta is small, you are getting the optimal MMSE. It's terrible, but you're getting it. And in the middle here, what's happening is, you're getting some MMSE that's up here, whereas the true MMSE is predicted by the replica method is much, much better, right? I mean, this is a logarithmic scale. So actually, for those of you who were in Henri's talk earlier, you can almost think that there's two thresholds here, right? Remember there was the threshold for where does water freeze, right? So one of these is like the water freezing at 0, and one of these is like water freezing at -48, if you want to think. And somewhere between these two thresholds is a difference between AMP is a practical, efficient algorithm. As to what it requires to get the MMSE, that's unknown. I can't give you any guarantees. All right, so this is one type of information. I should also mention, though, that this doesn't say anything about the mutual information. Right? Or at least not obviously. So in the case of this gap, this is not saying that you can use AMP to immediately find out what the mutual information is. It's a statement about MMSE. OK, but this still leaves open the possibility that the replica method is wrong, right? And that actually maybe this is the fundamental performance. So one of the ways I came to this problem is I was looking at support recovery, and I was trying to say, what are the fundamental limits of support recovery? That is finding, say, if you have a sparse signal, which entries are non-zero. And you do this, and you can reinterpret those kind of bounds on support recovery into these kind of MMSE domain. And what I showed there is that, in fact, so I apologize, the colors changed. But the key takeaway here is that this is kind of a figure which shows that the behavior predicted by the replica, which here is green, is tightly sandwiched between my upper and lower rigorous bounds, whereas the behavior of AMP is very different. So it's saying that there exist regimes in which AMP is behaving one way, but actually the optimal behavior is very different and seems to be in line with that predicted by the replica method. So this was rigorous evidence that indeed there is a different phase transition for optimal methods than there is for AMP. Another way of looking at this is if you want to attack the MMSE can be hard as a function of a given signal. But sometimes it's actually easier to study the behavior of a least favorable distribution in a class of signals for a given point in your parameter. That is, you look at these worst case bounds. So this figure is a bit weird to look at. The x-axis here is delta. And first look at these red lines. So these red lines come from me calculating the MMSE from the replica method for different choices of distributions that obeyed some sparsity constraint. So one of them somewhere is that Bernoulli Gaussian. Another one of them maybe is a mixture of Bernoulli Gaussians that have a requisite mass at 0. And as you pick different distributions, you get different kind of curves across this space. It's not like one distribution is always the hardest. And then these upper bounds correspond to different methods. And you can see that kind of the behavior of this minimax behavior is kind of tight, if the number of measurements is big or as you're kind of approaching kind of the spot where they're blowing up. But in general, right, there's still kind of a gap, right? And it's not clear, was I just not clever enough to find, pick a distribution and evaluate the replica at it, that the red line would be bigger, or is the analysis not tight? OK, so I should mention, if you do, as we talked about earlier, spatially coupled matrices, that is, you change up the matrix, you use a special matrix, you can, in fact, show then that you can get the AMP to have the performance as predicted by the replica method. Okay? So that does correspond to the fixed points kind of when you get over a hump and you can use spatial coupling. So that's super cool. The one potential issue with it is this is a special matrix, right? And kind of my desire from the beginning was to say I want to think about a large random or large typical dense matrix. And I think oftentimes a Gaussian matrix is a good measure of that. So you can see there's been some nice work where people have tried and said, here's analysis obtained under Gaussian measurements, matrices. Here's other matrices, and they have the same phase transitions. Okay? So the reason for studying a Gaussian was the hope that it would extend to more general classes of matrices. But these spatially coupled matrices are much more fragile, and you have to wait until the asymptotics kick in. So that's, I think, a difference. And I think there's also been work, looking directly at kind of the stability of the validity of kind of replica method situations using kind of ideas from random matrix theory, and this kind of work's been evolving over the last couple years. All right, so that's kind of the first part of the talk. I just wanted to give you an overview. What were the key points? The replica method's this nice tool. It's able to give a very precise description of the behavior of compressed sensing, and this description has some very nice properties, but it's not clear that it's rigorous, right? So some parts of it are understood, some are not. Yeah.
Just a quick question for you. You had a curve, this two threshold curve.
Yes.
So this is only for n to infinity, right? That's MMSE of the AMP equals MMSE of ideal MMSE.
That was the last part. That
yes, can go back to this with the two threshold. Yes. So you have the curves are identical except for the. But this is for n to infinity, right? It's not a statement kind of make statements about finite length. All these statements about n to infinity.
So the statement for finite length would be the following: is that the trick is how are you going to normalize this x-axis? Here, this is the ratio of m divided by n. I said n to infinity. For finite length, what you're going to see is that indeed there's some scaling under which these are continuous. But when you renormalize them as you increase n, they're getting sharper and sharper and sharper, and they become then these discontinuities. So for any finite length, no, it's not strictly speaking discontinuity, but it's becoming closer and closer.
No, but I mean, I did that you have that the curves are identical for large
yes.
delta or small.
Oh, you're saying that this equality holds only in the limit, and for finite lengths, there's some wiggle. Yes.
So there is a gap in finite lengths.
Oh, I think of those figures I showed at the beginning of the convergence of the mutual information for the random matrix. There could be some, wiggles in here due to the randomness of the instances. Are we taking expectations? Are we taking typical? Are we taking the saying right around the median? But I think as the randomness gets squeezed out, I would expect these differences are quite small, and it seems that if you can plot AMP, so here, you can plot AMP and it lines up pretty well with this, and you don't have to have the signal size be very large, and you don't have to run that many iterations.
I mean, you could compare instance by instance. You could compare, but even there you would.
Yeah. I mean, so empirical results for AMP match pretty well with the theory for IID Gaussian matrices. For spatially coupled matrices, it becomes more sensitive. So that's kind of the point I was making.
So the replica method is very hard to compute at finite length. So the thin curve at finite length is very hard to compute.
Okay. So the second part of the talk. Oh, yeah.
I have a question about the other belt.
Yeah.
2 slides later.
This one or?
This one.
Yeah.
So I didn't quite understand. So did you mean that the blue curve would somehow resemble the green curve at a different threshold, after a different threshold?
So you're saying threshold? What threshold?
So the reason they're very different is because within different thresholds they act differently, but they would act.
But thresholds on what? On the.
On the
Yes. I'm evaluating. So this is sorry, I didn't want to go into it, but the x-axis here is S and R, and I'm evaluating it exactly between those two thresholds, where I expect the difference to be different. Yeah.
So they would look similar.
Yes, absolutely. Yeah. Right. Yes. Yeah. So the purpose of this is to show that actually you can prove rigorously that in this region where the replica says we think you can do a lot better than AMP, you can show using other methods that yes, indeed, that is the case. But outside, if I evaluate on the other sides, then the blue would match up with the green.
So when your SNR is 80 dB, it means that basically you have no noise, right?
It depends a lot on how you scale it. I mean, it's a matter of these. Well, I mean, I'm not gonna. I can't say what 80 dB is or is not meaningful noise. I think the right way to say it is for any fixed noise levels, you blow up the signal, right? It's talking about here it's some error rate as a function of this noise. And so a lot of times when people.
There is no noise, 80 dB.
No, that's fine. I mean, look. Let me tell you a different point of view. a lot of the scaling results people give, in this regime, they'd say you need m equals k log n. And that would mean that the ratio between measurements to unknowns is tending to infinity. Or another thing I've seen many times, people say your SNR must scale with some log or maybe even a log-log term. And that's truly, in this regime of this limit, would be infinite SNR. So this is saying, look, this is everything scaling linearly, whether you want to think the actual parts in the plot are reasonable or not. It's a statement about if you had a problem at there. It's not a scaling result where you actually would have, under a lot of scaling results, infinite noise. Right? So there, I mean, I'm not saying whether this applies to your setting or not, other than just how it should be interpreted.
But this maybe somehow implies that even in the limit of infinite SNR, AMP still wouldn't be constrained, right?
Yeah. So I mean, yeah. These are this is a log scale here. I mean, this
so
is.
Even if you turn up the SNR and you really had zero noise, AMP wouldn't get the right answer.
Or maybe another way of saying it is even if you call, if we were going to say that 80 dB is no noise, the fact is that your error rate is still bounded away from 0. That is, you're still going to make errors. So you can't get exact recovery, or you can't even get recovery with a vanishing fraction of errors in support recovery. All right, so that's the first part. The second part, something new. Not this yet. OK, so this is something very new work I've done in collaboration with Henri, and it is our attempt to show that, in fact, the statement of the replica method is correct for this problem. And the approach we're going to take is not to use the replica method and not to try and verify those assumptions, but is actually, well, we'll see. It's going to be somewhat non-asymptotic in approach. So return to the replica. This is what I showed you before, and I said, remember these properties of the replica solution. One of them was evaluate the term inside the brackets, set the derivative equal to 0, we have a fixed point equation. There's another property we have here. And this kind of comes from the saddle point theorem, I believe, is that if we take the derivative with respect to the left-hand side. So here we have a function delta, but it's defined as the minimum of a function of s and delta. So when you take the derivative with respect to delta, what you get is that the derivative is equal to the derivative of the term inside with respect to delta evaluated at the minimizing s. So when we do that, and then we see some terms cancel out, we find that the derivative of the replica mutual information with respect to our delta parameter can be characterized as 1/2 log 1 plus m replica. Right? And that was actually the scaling I showed you in that figure. So this is our second constraint. There's I'll call this sometimes usually the derivative constraint or the integral constraint, depending on whether I'm taking the derivative or integrating it. What does it mean? Well, the first thing we can ask is, do these constraints alone kind of give us enough, an equivalent characterization of the replica method prediction? To do that, we go back to our figure here, right? And we say, OK, let's assume that whatever the solution is, the true solution, it lives on this curve, on the set of solutions almost everywhere. That is to say that it's a decreasing function that obeys our fixed point condition almost everywhere. So that means in this picture it's going to have at least one jump, but at most one jump. So here's 3 candidates. The one in the middle is the replica, the ones where we jumped early, the ones where we jumped late. Okay? And if all we knew was that we have one jump, we're on this curve almost everywhere, and this is our curve, then kind of we say, well, now the question becomes, well, which jump is the correct jump? Right? AMP was another example. It jumped as late as possible. Maybe there's a really clever algorithm out there that jumps as early as possible. So what we do is we say, well, we have this integral constraint, which is we know, at least for the replica, if we knew this constraint was also true, then we could say, well, only one of these, if we take the integral, is going to give us the right boundary conditions. So one boundary condition we get for free. Mutual information with no measurements is 0. The other boundary condition is, what is the mutual information with very large delta? Well, it's not completely trivial to find that, but it's not actually that hard. Because as delta becomes very large, this is the setting of a super, super tall, skinny matrix. And so you can actually characterize the very large delta limit pretty precisely. So let's assume we have these 2 limits, and we know that these 2 statements hold for whatever the true limits are. Then this constraint plus our kind of large m limit boundary constraint turns out are enough, and the only solution that satisfies them is the one given by the replica method. So it's the only one jump solution on obeying these whose integral matches the large infinite behavior. Large measurement behavior. Okay? Yeah?
Can I ask perhaps a silly question?
Right. So, right. So in order to say that there's only one jump, I have to make the claim that this condition holds almost everywhere. Now, and that it's decreasing. So now the only option, so if I didn't have decreasing, maybe I jumped here, then I walked backwards down. Yeah. So if it holds almost everywhere and I'm decreasing, then once I jump down, I'm stuck down there and I jump once. And so, as I said, some distributions, this curve never comes back in on itself, right? So some distributions, like the Gaussian, you never have any ambiguities. There's no jumps. This Bernoulli Gaussian at high enough SNR has a jump. A question I've wondered about is, can you have more than one jump? I've never seen a distribution that has more than one jump, and I've tried. I've plotted a bunch of different distributions trying to make there be two humps. I have yet to see it. Okay? So what I'm going to talk about is going to work in the situation we have at most one jump. Is this idea clear? Right? If we can establish, so decreasing we know. That one's clear. If we can establish these hold almost everywhere and the boundaries, we're done.
But decreasing again is because essentially if you have less noise, you can do worse.
Yes. You can't get more measurements and then have a bigger MMSE.
You just not use the measurement.
Yeah. All right, so here's the proof outline. And what I just described to you was this part. There were three things we needed: the MMSE fixed point constraint, the mutual information MMSE integral constraint, and the large measurement boundary constraint. Combining them with the argument I just said in words gives us that we must have the asymptotic mutual information and MMSE match the prediction given by the replica method. So everything else in the proof is set up to say, can we show that these constraints hold? And so what I'll do over the next couple of slides is I'm going to show you a particular path, and that's this line. Because I think it's kind of interesting, kind of has the most perhaps interesting ideas in it. So we'll see. And so the first thing I'm going to talk about is that mutual information MMSE kind of derivative relationship. And how should we understand that, and when would we think it's tight? All right, so we on board? The first thing we're going to do is we're going to look at the mutual information. And before, I've been saying, OK, I want to express the mutual information as an integral with respect to its derivative. Well, at finite length, we just think of this as a summation. And not surprisingly, I'm going to use the chain rule for mutual information. So the name of this talk was Understanding the Mutual Information, or MSE, one measurement at a time. What I'm writing here is on the left is on my mutual information sequence, where m is the number of measurements. It's an increasing sequence. On the right, it's the sum of my mutual information difference sequences, which is the difference at measurements m plus 1 versus mutual information at m. But by the chain rule for mutual information, I can express it as the mutual information between my new measurement and the signal conditioned on everything I've already seen. And maybe sometimes people get bothered that I drop the conditioning on the future measurements of A. So here, A to the superscript says all the measurement vectors up to measurement, in this case, k plus 1. And that's because my measurement vectors for larger than k don't tell me anything. They're independent of the system. So until I acquire those measurements, I don't need them. OK, so this is our first decomposition of expressing the mutual information as the sum of these kind of mutual information differences. A second observation. If what's one way of thinking about your MMSE, right? That is kind of the average variance of the entries given the signal at a given time, averaged over the data. Well, it turns out you can also express it in terms of a centered measurement. So that is, I'm sitting here, maybe I've seen m measurements, and then I know the measurement vector I get for the next measurement, but I haven't seen it yet. I'm going to make my guess as to what it is. So that's this expected value. And then I'm going to say, what's the difference between my guess of the next measurement and the true next measurement? Well, it turns out that the variance of this random variable is exactly equal to my MMSE, or 1 plus my MMSE. So this is just a trick of saying that kind of how if you want the linearity of my new measurements, and there's a 1 here coming from the noise, but it's saying I can measure my MMSE in terms of the variance of a future measurement. That's the takeaway. So I'm going to combine these two ideas. So the first is, this is my mutual information increment. How much information do I have about the next measurement given what I've seen? It's the same as if I consider kind of my centered measurement, where I pull out the expectation, since that's a function of everything I've seen here. Expanded is a difference in differential entropies. And now there's two inequalities here, which you teach in a first course in information theory. The first one is conditioning cannot increase entropy. So reducing it, I have nothing but an upper bound. So here I'm saying, OK, now let me think about the entropy of this random variable once I've forgotten everything. So I centered it, and then I forgot about everything. And then the second is that subject to a second moment constraint, differential entropy is maximized by a Gaussian, the same variance. OK, so I applied the Gaussian, maximizes differential entropy. And immediately, I'm left with, well, I'm left with actually something that's 1/2 log times the variance of this. But from the previous slide, I just said the variance of the next measurement, given everything you've seen, is 1 plus your MMSE. So you get exactly, this upper bound is 1/2 log 1 plus MMSE. Or reinterpreting it in terms of these limits, right? It says if you think about this as a continuous function of delta, it's saying that that derivative relationship that popped out of the replica, well, in fact, using just these two inequalities, that's a strict inequality everywhere. So non-asymptotic. So where all n, that holds. There's no kind of, at least there's a one-sided bound, there's no wiggle room there. So the whole question, if I want to claim that this holds almost everywhere in the limit, remember that's my goal. I can't say it holds everywhere because we know we're going to have a phase transition somewhere. So the statements I want to make is that this inequality is tight almost everywhere in the limit. In order to make that statement, what I have to do is I have to say, well, when are these inequalities tight? Or when are they tight almost everywhere in the limit? All right. So that was step one. And the next game is saying, how can we understand when these inequalities are tight? And let's just think for a second. When are these tight? Inequality 1 is tight if and only if, kind of, after subtracting out the expectation, this new measurement's independent of the others. Right? That's mutual information is non-negative. Okay, so that n equal to 0 if they're independent. So somehow my measurements and stuff don't tell me anything more once I've subtracted out my mean. When's the second inequality tight? Well, that one's kind of clear. When the distribution of my new measurement's Gaussian. So what I need to say is that the distribution of my centered measurement, conditioned on everything I've seen, is independent of everything I've seen and Gaussian. And then I'm done. OK. So we just did this one. So the next statement we need is what I'll call a conditional central limit theorem for new measurement. Which is exactly conditioned on everything I've seen, it's Gaussian with the requisite mean. Oh, mean 0, but requisite variance. OK. So at this point, I say, well, how do you argue that a new measurement is conditionally Gaussian? So here's the setup. Think about U here as kind of a high-dimensional vector. And for this application, it plays the role of the error, the difference between the true signal and maybe my conditional expectation. But just think of it as some high-dimensional vector with mean 0. We obtain a projection with a random matrix A that's IID Gaussian, and we'll just add on some Gaussian noise. So my question to you is, if I give you the vector U, what is a conditional distribution of Y? Right? So it's a linear combination of the Gaussian terms in A plus Gaussian noise. Conditioned on U, Y is a Gaussian random variable with variance proportional to 1 plus 1 on n times the second moment, the squared norm of U. OK? So by construction, right, Y given U is Gaussian. But that's not the problem I have. I have the different problem. I want to say, under what conditions is the posterior distribution of Y given A Gaussian? Right? So if I say to you now, here's a projection. Oh, here's A, by the way. Is this close to Gaussian? And you're going to say, well, that depends. What depends on U. If your U is a point mass, not really. Well, then it's OK. Then it's a Gaussian with a given mean. But if your U is some discrete distribution, right, it might not be. It depends on the properties of U. Now, you might think there's certain cases, right? You say, well, what if the entries in U are IID? Well, then we know it's very much like a CLT. You say, OK, I'm taking a linear combination of a bunch of independent things. Yeah, it's probably pretty close to Gaussian. Okay, so if U is IID, now what about for a distribution? But for our application, U is going to correspond to the posterior distribution on our signal having seen measurements. They are no longer IID. They're coupled together. So now the question is, well, what if the entries in U are kind of dependent? And there's some, for which distributions on U can you say something about this being close to Gaussian? So this problem actually goes back to this work of Sudakov in the 1970s, who showed that, and then the question is that, you can think about this as A is picking a different projection of this high-dimensional distribution. Some of these projections could be very far from Gaussian, but some of them might be close to Gaussian, depending on the distribution of U. So which ones are close to Gaussian, which ones are far from Gaussian? And the main takeaway is that most are close to Gaussian. That is, most projections of a high-dimensional distribution under extremely weak conditions on that distribution are close to Gaussian. And that's our setup. We're going to hope that U satisfies these very weak conditions. we're going to take a projection of it with high probability. That new distribution will be close to Gaussian. So here's the theorem, if you will. It's bounding the distance between that posterior distribution of y given A between a Gaussian with the matched second moment in terms of some properties of our distribution. And the properties are essentially the variance of the square of the magnitude of u. This comes in necessarily. And the second is the Frobenius norm of the covariance. So translation for this term, this is basically the average correlation of the entries in our signal. So how does this, what should I say here? All right. So firstly, so this is another result that I think is interesting. One kind of fun thing about presenting it here is that actually the proof uses what's known as the Gaussian Pangkor inequality. Which is, that you can bound the variance of a function of a Gaussian by the expectation of the gradient. And I use this on the moment generating function. So I thought that was a nice bit. But the point is that what it's saying is that if you can control just these two properties of your posterior distribution on the signal, you can then claim this Gaussianity of new measurements. And as I said, this is the variance of the errors, and this corresponds to average pairwise correlation. So we're working our way backwards through the path. We've now figured out we had to connect the integral constraint to the conditional CLT. We have the conditional CLT, but we have to connect this now to kind of this weak independence of the posterior distribution of our signal given measurements. All right, so this last one, well, we have another trick again, and I won't go through the details, but remember how before I said we can think of our MMSE, you can express it in terms of the variance of a new measurement? Well, you can represent the covariance of your error in terms of the covariance between two new measurements. Right? So this, again, it just works out. This is property of taking these projections of your error. OK, so this is useful because now it says that's the quantity I want on the left, but I'm relating it to some property here, the covariance of two new measurements. Well, now you can further express this covariance by bounding covariance in terms of mutual information. Right? Mutual information is zero, covariance better be zero. Well, you just kind of like show then that you can say a bit more about that. And what we get is we're able to bound this covariance term we need in terms of the difference. This is actually the second order difference of the mutual information. So this is relating it now to the smoothness properties of my mutual information sequence. So at the end of the day, what I wanted was a bound, which said almost everywhere, all these things are small. I am obeying my integral derivative relationship. I knew it couldn't hold everywhere. I said I want this to hold almost everywhere in the limit. Where will it not hold? At a phase transition. What happens at a phase transition? The second order differences are huge. What happens when you're not at a phase transition? These second order differences are tiny. So I have a bound that holds everywhere except at phase transitions, which is exactly where it should and should not hold. So that's, in a nutshell, kind of that path. And I will leave it there and maybe just put this up but not say anything about it in case there's any questions.